Section 10.6, the kinetic molecular theory of gases. Now what we're going to do is we're going to talk about the theoretical underpinnings of the gas laws that we've worked with in the previous sections. The kinetic molecular theory of gases is really something that was developed by Ludwig Boltzmann and James Maxwell. They're the ones that did the most work on this. And essentially it's the following ideas. We can really kind of narrow it down to 4 ideas. The first point is that when you think about a gas is made up of a large number of tiny particles. That are widely spaced. Okay, they're very, very small, and they're very far apart from each other. You can think of like a solar system almost. If you think about a solar system, you've got the sun, you've got the planets. Look how far apart those planets are, very far apart from each other. The second point is that these tiny little particles are in constant motion. And that motion is random, meaning they're not moving to the right or to the left. They're moving all over the place randomly. Each particle moves in its own way. Okay? And that these particles undergo collisions. Okay? You know, the collisions, could be more detailed about it and say that these are elastic collisions, which means essentially that when they do collide with each other, the energy is conserved, meaning that if one particle comes in with a certain amount of kinetic energy and the other particle comes in with some amount, none of that energy is lost during the collision. Okay? So they collide with each other. The third point would be that there's no attraction or repulsion between these particles. So there's no attractive or repulsive forces. Between these particles. And then the final point is not an obvious one, but it's a very important one. It says that the average kinetic energy of these particles is proportional to the temperature of the gas. And just so that we're clear, when we talk about the temperature, we're going to use the Kelvin scale just like we have for the gas laws. Okay? So let's point out, well, actually, let me do this. Let me draw a little picture for you so you get an idea of what I'm saying. There's good animations online, but we'll point this out. So again, the idea is that these particles, it's a large number, so I'm not going to draw a large number. I'm not going to draw a mole. But I'll draw a few particles here just so you can get an idea. See how widely spaced they are? They're really far apart from each other and they're tiny, okay? The size of a molecule, size of an atom, 10 to the minus 9 meters perhaps in size, even a little smaller than that. They're in motion. Now, how do you represent motion? I'm going to represent it by using arrows. So this arrow is pointing in a direction. So let's say that that particle is moving in the direction of the arrow, okay? Let's say this particle is moving in the direction of that arrow. Now notice that arrow is a lot shorter than the first one. Let's call this 1 and this one 2. What we would say is that the length of the arrow is proportional to how fast that particle is moving. So which one do you think is moving faster, 1 or 2? Okay, The arrow for number 1 is longer, so it's moving faster. The arrow for number 2 is shorter, so it's moving slower. And they're moving in different directions. Now, we can't really tell, but it's quite possible they'll collide with each other, right? This particle is moving in this direction. This particle is moving in that direction. They might collide with each other. Transfer energy in that collision, change directions. What about this particle here? We'll call this particle 3. Okay. Is this one moving faster than 1 and 2 or slower than 1 and 2? Well, so far it's moving the fastest, right? It's got the longest arrow, so it's going to be moving the fastest. Now this one, let's say this one's moving, let's say this one moves in that direction, number 4. Okay, that one's moving in a different direction. And it's moving sort of in between, maybe a little bit faster than number 1, but slower than 3. Here's another one. Suppose this one's moving in this direction. There's number 5. This one might be number 6. Now I'm trying to draw these randomly, right? I said this random motion. So, meaning that there's no directionality. They're not all moving in one direction, or not even more of them are moving in a particular direction. They're moving in random directions, okay. Notice they will collide with the walls and then bounce off, right? So that can happen. Okay, so no attractive or repulsive forces, meaning that when this particle is over here and this particle is over there, they don't know each other's there. There's no gravity that's pulling them together, right? Now there is, I'm not going to claim that there's no gravity, but these molecules are so small, they have so little mass, gravity is negligible. Okay, we don't have to worry about it or concern ourselves with that. They're also not repelling each other like magnets do. Now, the last point is that the average kinetic energy is proportional to the temperature of the gas. And that's an important point. That's one that we want to talk about in a little more detail. If you recall, the kinetic energy of a moving particle is equal to 1/2, this is from chapter 5, times the mass of the particle times the velocity or the speed of the particle squared. Okay, this is 1/2 mu squared. Some textbooks will use a v for velocity, but we're going to use a u for velocity. Okay, but we don't have one particle. We have a lot of particles. So what do? What we do is we write it this way. I'm going to put a line above the E. Sometimes that's called a bar. So EK bar. That's the average. Okay? We talk about the average kinetic energy of the gas. Okay? We're going to do averages. So there is a type of average. You're probably most familiar with the simple or arithmetic average. But what we're going to do is we're going to talk about what's called the mean square speed. And the mean square speed, say that 3 times real fast, is u with a bar squared. Okay, so we're squaring something. And this is equal to the speed of the first particle squared plus the speed of the second particle squared plus the speed of the third particle squared, all the way until you get up to the last one. So let's say we have n particles. It could be 6.02 times 10 to the 23rd squared divided by the number of particles. Okay, so that's called the mean square speed. It's a type of average that we use in these calculations. Okay. Now, let's go a little bit further here, and let's talk a little bit more about what we call molecular speeds. So let me make a little space here. And I'm going to come back up here. And just write a simplified form of this. And that we call the mean square speed. Not mean as in not nice, but mean as in average. Okay. Now let's talk a little bit about more molecular speeds. Remember, these particles are in motion. So the first thing I'm going to do is I'm going to say that we have, let's say that we have 1 mole of particles. That's a convenient number, right? It's a convenient quantity because our balanced equations and our molar masses are per mole. So that's not a bad idea for doing it. So what I'm going to do is I'm going to say, suppose we have 1/2 mu squared, okay? Now where does that equation come from? Essentially 1/2 mu squared is the kinetic energy of one particle. 1/2 mu bar squared would be the average kinetic energy of a bunch of particles. Suppose we have a mole of particles. A mole is Avogadro's number, right? 1 mole is N sub A, and that's 6.02 times 10 to the 23rd particles. Okay? Now here's what I'm going to claim, and I'm not going to derive this, I'm not going to prove this, this is covered in more advanced courses. It has been shown that this is equal to 3/2 RT. And that's an important result of the kinetic molecular theory of gases. What it says is the average kinetic energy of a mole of gas particles, 6.02 times 10 to the 23rd particles, could be oxygen molecules, could be helium atoms, gaseous particles. That average kinetic energy is equal to 3/2 times the universal gas constant R times the temperature T. Okay? Now, generally, when you do calculations using this equation, for R, you want to use the MKS system value of R, which is 8.314 joules per mole Kelvin. This is the MKS. Remember, meters, kilograms, seconds? That's the MKS system. It's also the SI system, units for R. So it's not 0.08206, although you could use that if you were careful in your calculations. But generally, we're going to use this value of R, 8.314. We're going to keep it in the MKS system. And let's point out that when we do temperature calculations, it's going to be in the units of Kelvin, not Celsius. Don't leave it in Celsius, okay? Put it into Kelvin. So this over here on the left side is the average kinetic energy of all these particles in the box that are bouncing around. And what we're claiming, this is really 0.4 of our molecular theory of gases. It's equal to 3/2 RT. And that's powerful. So what if we did the following? What if we pointed out that N sub A is a mole And so I took this equation here, and I notice that there's a half on the left and there's 3 halves on the right. So I can get rid of the half, right? So that would be n sub a times m u bar squared equals 3RT, right? Because that half is on both sides. 3 halves is the same as 3 times a half. Now, what if I then said I want to rearrange this equation and solve for the average speed squared? Okay, so I want to get u bar squared. So what I could do is I could point out that m sub a is a mole. Okay, so I could now substitute in for this. This would be the same as the molar mass. Because m is the mass, n sub a is a mole, so n sub a times m is the molar mass. Okay, n sub a is actually the number of particles per mole. So the mass times the number of particles per mole would give you the mass of 1 mole, which is the molar mass. Okay, so let me substitute that in there. So now we have molar mass times the average speed squared is equal to 3RT. Now what I'm going to do is I'm going to divide both sides by the molar mass. Nice. So now what this says is that the average speed squared, the mean square speed, we called it, right? That is now equal to 3RT over molar mass. But what if we want to know just the mean speed or the average speed? We would take the square root of both sides, right? Because we have a square on the left. So let's take the square root of both sides. So now we get the mean speed, not the mean square speed. Oops, sorry. I just said I was going to do something and I didn't do it. Let's get rid of that square. The mean speed is now equal to the, because you have to take the square root of both sides, right? That's equal to 3RT over molar mass. And here's one of our results. Now, because we took the square root of the mean square speed, and remember how we calculated that, I'm going to put RMS in there. RMS is root, because you're taking the square root. Mean is the average. Square, because originally you squared each velocity. It's not a big deal if you don't fully understand that. It's a mathematical issue. But the point is that there's a type of average, a type of mean called the square mean. And we're trying to find the square root of that, so we call it the root mean square. But it's essentially a measure of the average speed. The average velocity, the URMS, is the square root of 3RT over the molar mass. So if we know the molar mass of the gas, and we have the value of R, and we know the temperature, we can find the average speed of these gas particles in a collection of gases. So what I want to do at this point is I want to show you a couple of graphs to show you how this plays out. So I'll rewrite this final result over here up at the top, but then go over the graphs. See if I can get rid of this like that. There we go. Okay, so the result we had was URMS is equal to the square root of 3RT over the molar mass, right? There we go. Okay, so a couple of interpretations of this. One is, how does temperature affect the average speed? So what I'm going to plot here is number of molecules on the y-axis. And then on the x-axis, I'm going to write out molecular speed. How fast they're going. And this one, for this graph, we're actually going to have units, meters per second. Okay, speed is meters per second. So remember, speed is distance traveled divided by time. So meters is the unit of length, distance, and then seconds is the unit of time. And what I'm going to do is I'm going to show you distributions for several different temperatures. I'm actually doing figure 1020 from your textbook. Okay, so you can look up that figure and get a little bit better picture. So I'm going to start off with a lower temperature. So this is sometimes called a Boltzmann distribution. And this is at a temperature of 100 Kelvin. Pretty low temperature, negative 173.15 degrees Celsius. Now, this is for nitrogen. And take a look at that distribution. And I'm going to put some numbers in here. So this is 0. The slowest they can move is 0. This is 500. And then I'm going to actually go out further here to 1,000 and then to 1,500. Okay. Ooh, there we go. I'm going to extend it a little bit further. Okay. Now, the average speed, the RMS average, is probably somewhere around here. It's a little bit to the right of the peak because you have some more molecules to the right than you do to the left at the peak. It's not a symmetric distribution. So that's how fast they would move. So some of them are moving 500 meters per second. More of them are moving about 200 meters per second. If you double the speed in meters per second, you get an approximation of miles per hour. So 500 meters per second is 1,000 miles an hour. Okay. Now what I'm going to do is I'm going to increase the temperature up to 300 Kelvin. That's like a nice warm spring day, 27 degrees Celsius. Okay. It's the high 70s, maybe even 80 degrees. Okay. So as long as it's not too humid, that's okay. 300 Kelvin, and you get something that looks like this, approximately. There's your 300 Kelvin. Look what happened to the distribution. So the mean is now up over here. It's up higher, right? Okay. They're moving faster. Now you may notice that it's gotten shorter. The reason it's gotten shorter is that we've spread things out. So they're spread out to higher velocities. So there aren't as many moving at any particular speed because they're moving over a wider range of temperature or wider range of speeds. But they're going faster on average, right? Again, this is your URMS here. Okay. And then finally, suppose we did even 700 Kelvin. You get something that looks like that. So at higher temperature, they're moving in faster. So now take a look what's going on in terms of this equation. Where is temperature? Is it in the numerator or the denominator? It's in the top, right? It's in the numerator. So if you increase the temperature, the right side of the equation increases, so the left side of the equation has to increase. So the average speed is going to go up. So where's the average speed out here? I don't know where it is. Maybe it's like right there. Now, obviously, that equation can't give you the entire curve. It can only give you one value, which is URMS. The way you would get the distribution is through more complicated equations. So the distribution, I'm just giving that to you, this whole shape of the curve. The only value you get out of this calculation that we're showing here is that RMS, okay? Now, that's the relationship between temperature and the speeds of the molecules. There's another thing we could look at, which is how heavy are they? What are their molar masses? Are they heavy or light? So again, we're going to do another graph here. Let me see if I can make this a little bit bigger. Here we go. And now what we're going to do is same number of molecules. And then on the x-axis, we're going to do molecular speed. So let me put that over here on the right. Molecular speed. And again, this is in meters per second. And let me put a couple of numbers over here. We'll go up to 2,500, I guess. So 500, this is 0 over here. 1,000, trying to make them evenly spaced. 1,500. Remember, you essentially you double the speed in meters per second to get miles per hour. So if you're up at 2,500 meters per second, that's over 5,000 miles an hour. That's pretty fast, right? Faster than a bullet. Okay, so now let's do 3 different gases. The first gas I'm going to do is a relatively heavy gas, chlorine gas. Okay, so chlorine gas will be like, it'll give us a distribution that looks something like this. So this is a heavy gas. It has a molar mass of 70.9 grams per mole. So that's its distribution. Now let's compare it to nitrogen. Suppose we do nitrogen. Nitrogen doesn't weigh as much as chlorine. It's 28 grams per mole. Now how did I know that? I hope you still remember. You look in the periodic table, right? Cl2 and N2, you look them up. Okay, so notice the nitrogen is lighter. The distribution is moved to the right, so they're moving faster on average. Now, in fact, even if the gas is heavier, there's a chance that the molecule in nitrogen is moving slower than a molecule in chlorine, right? Some of the nitrogen molecules are way over here. They're moving slow. Some of the chlorine are way over here. They're moving fast. So we're not claiming they're all moving faster if it's lighter. We're just claiming that on average, they're moving faster, okay? And then finally, let's put in helium. Helium's a really light gas. It's the second lightest gas there is in nature. Ooh, look at helium here. Helium has a molar mass of only 4 grams per mole. So it moves faster. Again, some of the helium are moving slow, but some of them are moving fast, thousands of miles per hour. Okay, so why is that? Because of this equation. Molar mass is in the denominator. So the heavier they are, it's in the denominator, the smaller the RMS is going to be, the RMS speed, I should say, the root mean square speed of these molecules. So the distribution, again, widens because they're moving faster, so some of them can move really fast, so it gets shorter, but it's moving to the right, faster molecules. So 2 relationships, temperature and molar mass, that you should be aware of. As a gas heats up, if you make it hotter, the molecules move faster on average. If you make the gas molecules heavier, but at the same temperature, they're going to move slower on average. Okay? So that's a nice relationship. 2 relationships, actually. Now we'll take it a little bit further to look at an interesting situation. And that is this relationship between ratios of the speeds. Again, when we say speeds, we mean the RMS speed, the average speeds. It's a very simple relationship. So suppose I have 2 gases. And we're going to call them gas 1 and gas 2. And we're going to mix them together and ask how fast are they moving. Well, let's do this one. Let's do U RMS of gas 1 is equal to the square root of 3RT over the molar mass of gas 1. Right? I guess I don't need such a big radical sign. There we go. And what about our second gas? So our second gas, whatever it is, could be heavier, could be lighter. This one is equal to the square root of 3RT over its molar mass. It's a mixture of gases, so they're in the same container. If 2 gases are in the same container, they're going to have the same temperature. Okay, that's an important point. Now, suppose I took the ratio of these 2. How much faster is one moving the other, for example, or how much slower? Well, then I would take the ratio over here as well. But if you take a look, a lot of things cancel. This cancels with that, this cancels with that, this cancels with that, and you end up with this simplified ratio. Oops, I skipped a step that I haven't really talked about, so let me go back a little bit here. So you get the square root of 1 over the molar mass of gas 1 over the square root of 1 over the molar mass of gas 2, right? Because we can cancel the 3 RTs. Well, that's pretty awkward looking, right? So here's what we could do. We could multiply this by 1 over the molar mass of gas. Actually, I'm going to come back here. Let's not do that yet. Let's do this. If you have the square root of something divided by the square root of something else, that would just be the square root of the ratio. There we go. Oops. There we go. Much better. So now let's do the following. Let's multiply this by, inside the radical, molar mass of 2 over molar mass of 2. Molar mass of 2 over molar mass of 2 is 1, so we're not really changing anything. However, look what happens when you do that. You get the square root of m2 over m1 in the top over, sorry, this needs to be a little bit taller here, over m2 over m2 on the bottom, right? So this one goes there, so it's m2 over m1, and then this goes here, so it's m2 over m2. Well, m2 over m2 is just 1, right? So that means that this ratio is equal simply to the square root of m2 over m1, the molar mass of gas 2 over gas 1. Okay, so that's a nice result. What that shows is that the ratio of the average speeds, gas 1 to gas 2, is equal to the square root of gas 2 divided by gas 1. Notice it's the reverse. 1 over 2 is equal to 2 over 1. So let me come back here and make some room and show our little result here. So what we have is that the speed, the average speed of gas 1, divided by the average speed of gas 2 is equal to the square root of m2 over m1. Okay? So if we had, for example, 2 gases, let's say gas 1 is helium, and it has a molar mass of 4 grams per mole. And gas 2 is, I don't know, let's make it carbon dioxide. And its molar mass is 44 grams per mole. I'm just approximating here, right? What would the ratio be? The ratio would be the speed of the helium divided by the speed of the carbon dioxide. Average speeds, right? RMS. I'm taking the RMS out just to make it a little simpler looking. That would be equal to the square root of the molar mass of carbon dioxide, 44 grams per mole. Remember, it's the reverse. Whatever it is on the left, it's the reverse on the right. Divided by the molar mass of the helium, 44 grams per mole. So that would be the square root. Units are going to be gone, right? 44 over 4 is 11. Okay? So what does that equal? Well, that's like 3.3. So what that tells us is that this ratio, the average speed of helium atoms compared to the average speed of carbon dioxide molecules is about 3.3. We would interpret that as meaning that on average, if you have a helium atom in a particular time unit, let's say a second or a millisecond or a microsecond, if you compare how far it travels to a carbon dioxide molecule at the same temperature in the same amount of time, the carbon dioxide molecule will travel much smaller distance. The factor would be 3.3. So if it travels a distance of 1, the helium atom would travel a distance of 3.3. That's how much faster it's moving on average, okay? This equation is sometimes referred to Graham's law. So if someone asks you to do a calculation involving Graham's law, that's this equation right here. Okay? And there you go. So that is that's one application of the kinetic molecular theory of gases.